In this episode, we dive into three striking advances, pushing AI beyond its usual limits. A new way to ground language in segmentation by predicting concepts instead of tokens. A foundation model that finally brings hyperspectral Earth observation into large-scale, multimodal pre-training, and a training-free video editing method that turns streaming generation into precise, few-step visual transformation. Together, these papers reveal how AI is becoming more semantic, more multimodal, and more controllable than ever. Let's explore the first paper, SetCon towards open-ended referring segmentation via set-level concept prediction. SetCon reframes open-ended referring segmentation as explicit set-level concept prediction instead of the standard per-target SEG token interface used by LVLM-based models, such as LISA, PixelLM, and SA2FA. The paper shows that flat SEG sequences degrade sharply as target count increases, and that learned SEG embeddings align more with spatial position than semantic category, causing duplicated or missing masks. SetCon replaces these tokens with natural language concept spans generated by a Qwen3 VL8B instruct backbone and uses their hidden states as semantic conditions for joint mask set decoding with SAM3, adding a hierarchical decomposition that first predicts one global set concept and then finer subcategory concepts. To train this interface, the authors build a two-stage annotation pipeline with Qwen3VL235B A22B, producing 236,396 samples and 784,809 concept phrases. With hierarchical supervision over 80% multi-subcategory cases, on image benchmarks, SetCon reaches state-of-the-art performance on gref Coco and Muse, improving by 3.3 GIOU and 12.1 GIOU on their validation sets, respectively, while remaining competitive on RefCoco plus G and achieving the best average on ReasonSeg. On video, it sets new state-of-the-art on 7 benchmarks, including plus 10.9 JNF on Mevis and plus 12.4 JNF on RefSecVos. The key novelty is that semantic concepts, not special tokens, become the interface between language, reasoning, and mask prediction, making multi-instance and cross-category grounding both more interpretable and more stable. Let's explore the second paper, Spectral Earth FM, bringing hyperspectral imagery into multimodal Earth observation pre-training. Spectral Earth FM is the first multi-sensor Earth observation foundation model to bring spaceborne hyperspectral imagery into joint pre-training with multispectral imagery, synthetic aperture radar, and land surface temperature. Its key novelty is a hierarchical transformer that preserves hyperspectral structure through sensor-specific spectral tokenization, then fuses modalities with projected attention before a shared Hyera trunk. The model is pre-trained on Spectral Earth MM, a new corpus of about 2 million globally distributed locations, 25 million georeference patches, and more than 40 terabytes of data built from Nmap, EMIT, and DCIS hyperspectral missions aligned with Sentinel, 2, Landsat 8, 9, OLI, Landsat LST, and Sentinel-1. Pre-training uses a JEPA-style latent prediction objective, with an EMA teacher producing stop gradient targets from 2 global multimodal views and a student matching those targets from global and sensor-dropped local crops. A SIGREG penalty prevents representation collapse. On 10 hyperspectral benchmarks under the Spectral Earth protocol, Spectral Earth FMA achieves the best overall average rank, 1.4, and Spectral Earth FMS reaches 2.5, beating specialized hyperspectral baselines such as Spectral VTL, Hypersigma, DOFA, and Carl. On the Pangaea General EO Suite, the multimodal variant also ranks first overall with an average rank of 3.43, showing that hyperspectral pre-training can improve transfer without sacrificing performance on standard optical and radar tasks. Let's explore the third paper, Stream GVE Training, free video editing via few-step streaming video generation. Stream GVE reframes training-free video editing as source condition noise-to-data streaming generation, instead of the usual data-to-data inversion pipeline that needs many iterations and accumulates error. Built on pre-trained autoregressive streaming generators such as self-forcing and long-live, it performs dual-branch few-step sampling. The source video and target video are denoised in parallel under shared noise, then a self-attention bridge blends queries and keys to preserve structure, motion, and background while still allowing semantic change. For precise edit localization, Stream GVE derives masks from cross-attention grounding using foreground-background attention differences over trigger words, and then applies cross-attention boosting with a tunable strength omega to amplify edits only inside masked regions. It also adds source-oriented guidance, which corrects stochastic drift in editing irrelevant regions by projecting source branch velocity error onto the target branch, and an optional visual prompting mode that uses an edited first frame for finer control. On 5bench, StreamGVE achieves the best reported 5 EAC at 61.19 with long live plus visual prompting while running at 0.6 to 0.76 seconds per frame in 5-step settings. Without prompting, Hours SF reaches 51.94 5EA, and Hours LL reaches 55.04. The method generalizes to long videos over 470 frames and ranks first in user studies for quality, background consistency, and editing fidelity. That's a wrap on today's AI paper highlights. Thanks for watching.